Testing 1, 2, 3. All right, so let me get the PowerPoint started here. All right, so my name is E.J. Daigle, the Dean of Robotics and Manufacturing here at Dunwoody College Technology. And next topic will be a basic introduction to variable frequency drives. We will, in the lab, we'll be using ABB's ACS150 drive. And well, we'll get into it now. So when we talk about industrial networks, an industrial system, whether it be in a plant, wastewater control, controlling an elevator, it could be anything really, packaging machines, any of that stuff. A lot of times what we talk about is, or what the operator interfaces with is the human machine interface. This is where you can start and stop machines, you can turn things on and off, you can get status of things and do all kinds of various things. Well, the HMI sends its signals over to the PLC. The PLC then is really the traffic cop. He's the decision maker. In addition to getting inputs and sending data to the HMI, the PLC is also getting inputs and outputs to real world devices. Switches and sensors, push buttons, light trees, and output field devices such as motors and fans and pneumatic solenoids and things like that. All of that's happening. But in a lot of cases, we need to run motors. And unless we're just turning a motor on or off, or in the case of a DC motor, we're using a DC drive, it's very common for us to be using what are called AC drives, or VFDs. That's this guy right here. And the beauty of the VFD is the VFD allows us to control AC induction motors, like this guy right here, very, very precisely. So it's not like a servo where we're concerned about shaft position or something like that, but it is about wanting to control speed, let's say. So let's say we have a pump and we're trying to fill up a tank, and the fluid in the tank is being used very rapidly. We would want to fill the tank very rapidly. Let's say the tank is being the fluid in the tank is being used very slowly. We might want to run that pump at a slower rate. So the ability to control that pump at a very, very precise level is very important. Kind of bounced around there for a second. But the other thing too is not just controlling speed. We also like to control things like direction. We also like to control things like ramp up and ramp down times. So I might want to, to protect things like chains and belts and pulleys and bearings. I may not just want to hit it from 0 to 1800 RPMs instantly. I may want to slowly ramp it up, so those gears and belts and pulleys kind of have a chance to tension up and, take on the load without it just hitting all at once. Kind of like driving your car. You don't typically, when the light turns green, I hope you don't just floor it and just go until you hit 55. Probably what happens is you kind of feather into the gas pedal, and then you feather back off of the gas pedal when you want to slow down as well. All right, so when we're controlling motors, there's a number of different things that we want to use. So the first one that we've worked with in the lab was the motor starter. Motor starter is basically just a relay is all it really is. The difference between the motor starter and a relay is that we have the relay portion, or the contactor, but then we also have this overload protection down here. So we're constantly monitoring the current, and if for some reason we try to send an overload condition to the motor starter will trip out. It'll break the control circuit, just like a stop push button would. And then we can troubleshoot, figure out what happened, why did this happen, and it's much better for the motor starter's overload to trip out than to burn up $1,000 or a $10,000 motor. So that's why we use overload protection and not just use a contactor directly. We could control a motor with a contactor directly, but the overload provides us some protection. The trick with a motor starter, though, is what if we want to reverse a motor? Well, the only way to reverse a motor is really to have two motor starters then. I would have motor starter 1, and I'd have L1, L2, and L3 that would get sent down to the motor. But now, I might call this my forward motor starting. But to reverse a motor, I would have to have a second motor starter. So I'd call this my reverse motor starter, motor starter number 2. And what I would do is I'd switch two of the leads, L2, L1, L3, coming in. But they would go down to the motor in the same fashion as these other ones would. So now L2 would go where L1 used to go, and L1 would go where L2 used to go. and L3 would still go to where L3 was going. But you can kind of see how that works is, you know, it's T1, T2, T3, and T1, T2, T3. So as I'm running L1, L2, L3 through this motor starter, they go down directly T1, T2, T3. But if I'm running the reverse motor starter, L2 goes to T1, L1 goes to T2, and L3 goes to T3. It's a very common practice. If I just want to control the direction of a motor, to have two motor starters, and it's going to work fine. The danger in here lies in you need to protect, kind of like an exclusive OR gate, make sure it's not possible to turn both motor starters on at the same time. Because if you turn both motor starters on at the same time, you essentially would be shorting out your phases. L1 and L2 would short directly, L2 and L1 would short directly, and that would be very, very bad. But again, very common practice, very easy to prevent having both on at the same time as well. Another particular control that we can use is the reversing drum switch. That's this guy over here. And the reversing drum switch is probably the simplest way to control the direction of a motor. You don't need two motor starters. I can just use a reversing drum switch to go back and forth. The neat thing about this guy is, let me move this guy out of the way for a second. You'll see 1 goes to 2, 3 goes to 4, 5 goes to 6 in the reverse direction. In off, nothing gets connected. And in forward, 1 goes to 3, 2 goes to 4, and 5 goes to 6. What that means, if I look at the next slide here, come on now, wake up. There we go, is exactly what we just saw. I run L1. There we go. I run L1 here. He comes into 2. L2 gets wired up to 3. L3 gets wired up to 6. It's the same for reverse and forward direction. What's really happening internal with the drum switch is we're making the connections different. In forward, 1 to 3, 2 to 4, 5 to 6, and in reverse, 1 to 2, 3 to 4, and 5 to 6. So these mechanical contacts switch positions internally. And what I like about tracing this guy out is let's just take a look at forward for a second. We're not going to trace all of the currents, but if I look at forward for a second, I come in here, I go to there, I go down, I go around, and then I go up to T1. So I go up to this first motor coil. Notice the direction of current flow on this coil here. And I go back, and I go down, and I go back out. We can see the direction of current flow on T1 here is in this direction, right? I think everybody can see that. Let's do the same thing with this switch put in the reverse position. Now I can see this thing goes out like this, goes out like this, boom. Now I go this direction through T1, and I go back in this manner. 5 and 6 never change, so that doesn't matter. But as soon as I've swapped 2 leads, we know this from the 3-phase motor starter as well, as soon as I've swapped 2 leads, I've changed direction of the motor. So the reversing drum switch actually does that for you. You wire it up one time, and internally it swaps 2 of those leads to make sure the direction of current flow through your coil there. And then imagine your motor shaft is in here, and in this way maybe it spins this direction, and on this example maybe it spins in this direction because that rotating magnetic field is pushing that shaft. And you know, those are 2 of our most common, and used to be that those were the inexpensive way to control a motor. So if I wanted to control, let's say, a 1 horsepower motor, I might go out and buy a reversing drum switch and go forward or go reverse. And the reversing drum switch could cost maybe, I don't know, $150, $200 or something like that. And you'd say, wow, that's pretty cheap by comparison to the variable frequency drive, right? Because VFDs used to be very, very expensive. What's funny about all of this, and motor starters as well, you know, motor starters might say, oh, why for, you know, $120 I can get a motor starter, and for $250 I can get 2 motor starters. Now I have direction control, overload protection, I've got all kinds of stuff, right? And that was true when VFDs were really, really expensive. But what I would tell you is VFDs are now comparable. If you wanted to control a motor and you're going to go buy a drum switch as an example, you might spend $250 on a drum switch. I'd venture to say for the same, you know, for a 1 horsepower VFD, you know, for probably $300, you can get a pretty nice 1 horsepower VFD and have a lot more control than just direction. So a variable frequency drive, or VFD, also known as a variable speed drive, an AC drive. We also call it an inverter as well. You'll see why here in a minute. I'll talk a little bit about that. It's a type of AC motor controller used to control motor speed and torque by varying frequency and voltage, and so much more. so much more. This little control panel that you see on this VFD means I can control the motor from here. I can input all kinds of different parameters. I can do ramp up, ramp down time. I can do dynamic braking. I can do SCurve functions. I mean, there's all kinds of, it's, you know, for the amount of features you get, the VFD is way cheaper than even a motor starter, just because you get so many features for maybe $200–300. So some of the benefits over a manual control like a starter or a drum switch: energy savings. I have precise control. I can ramp up, I can ramp down as needed. I don't need to run full speed. I have precise control over speed and torque. So another thing that we haven't talked about, but like a soft starter. A soft starter would allow me to ramp up slowly. But the problem is once I'm up to speed, all I can do, I can't change speed again with a soft starter. A soft starter, I can ramp up slowly, but then if I want to change speed, you know, all I can do is shut down and ramp up slowly again to full speed. You know, a VFD on the other hand, I can ramp up, ramp down. I can go from 1800 to 900 RPMs to 230 RPMs to 460 RPMs in the reverse direction. I have complete control over everything. So that goes back to that ramp up, ramp down time, closed loop feedback to the PLC. I can send a signal back to a PLC telling the PLC, hey, look, you told me to go 1800 RPMs. I'm only going 1750. The PLC then can do a PID algorithm to determine how to close that gap. I also have programmable overload protection. So I can set in there motor nameplate data and have the VFD monitor for overload conditions, over voltage, over current, you know, all kinds of different features there. So what's inside the VFD? So if you look at the guts of a VFD, we'd supply a VFD just like we would a three-phase motor. You know, you have L1, L2, and L3 coming in. And I should say this, I want to be careful on this, and then you have T1, T2, T3 coming out. I do want to be a little careful on this though. There are VFDs. Here's another benefit of a VFD. You can get a single phase VFD. So let's say in your garage, you have 240 volts single phase, but you just bought a machine tool or something that needs three-phase power. You can actually use a single phase VFD to create three-phase power. It's one of the most common ways to bring three-phase into a residential garage is to hook up a drive as a feature. And actually in our lab, actually our VFDs are 240 single phase. But most VFDs you're going to find are three-phase in, three-phase out, just like a motor starter. The first thing that you're going to see inside, and you'll never rip one open, but if you ever did, first thing that you're going to see is a converter or a rectifier. Essentially in there's a bunch of diodes, and those diodes are used to rectify the AC voltage coming into a DC voltage. You know, you imagine diodes take AC that looks like this, and they basically rectify it into DC that looks like this. And then eventually they'll also filter it so that you end up with a nice smooth DC that looks like that, you know, something like this. But that's what's happening. We're taking the AC in, we're creating DC out of it. And now the DC bus is what's going to filter out any of that ripple. So this would be ripple here. And this would be a smooth DC right here. And then the interesting part, where the magic really occurs. So all we really did was create a DC power supply so far, right? AC coming in, DC coming out. But where it gets really interesting is the inverter side. The inverter does kind of what you'd expect. So if you buy an inverter for your car, you plug it into a 12-volt DC receptacle in your car and you get AC power coming out, which works very similar to what we're going to do with this VFD. But the difference now is inside of this inverter section, there's a bunch of transistors. And what these transistors do is they act like switches, and they switch on and off to create what's called a pulse width modulation waveform. So this PWM stands for pulse width modulation. And what that is it's a way to fire DC switches in such a way that we can represent an AC waveform. And to show you what I mean is, imagine these are DC switches firing in positive and negative directions. And so like this DC switch here is turning on for just a short period of time right here, right? And this DC switch is turning on a little longer, and this DC switch is turning on a little longer and a little longer, eventually to where they're almost on all the time. Well, if you see what this really looks like to the current, is it really looks like an alternating current. because the average of this little pulse is just a little bit, and the next pulse is a little bit more, and the next pulse a little bit more. By the time it's all the way on, the peak of your waveform is way the heck up here. So you can kind of see how I can create an AC waveform from a DC voltage. Now what's interesting is, let's say you gap these differently, right? So you let's say up here now you're turning on, and then down here you're doing it different. What you can see right here is I might have the exact same height of a waveform, but what am I doing? I'm doing it more often, so I'm getting a different frequency. So this is upping the frequency, and this would be downing the frequency. You know, if I'm looking at the same amount of time, you know, I can squish this thing together by firing faster, or I can spread it out by firing those transistors slowly. So the frequency at which I fire those and the duty cycle, how long I keep them on, determines the frequency of that waveform. So it's a pretty cool deal as to how we use a digital signal to create an AC waveform is essentially what we're doing. So hopefully that kind of gives you the idea. These transistors down here are firing, and what I'm doing is I'm getting a waveform that looks like this, or I'm getting a waveform that looks like this. Same peaks, higher frequency, or maybe I'm getting a waveform that looks like this, really low frequency. All of those are directly proportional to the speed increasing or decreasing. Okay. Now, when we talk about that frequency being directly proportional to the speed, there's a nice little formula that we can use to convert this. It's called synchronous RPMs, or no load RPMs. We take a constant number 120, we multiply it by the frequency, and we divide it by the number of motor poles. These things, you know, the frequency we can adjust, typically between 0 and 60 hertz. The number of motor poles we can get from the data sheet for your motor. A lot of the information you can get right off the motor nameplate, but you may have to dig in a little deeper to get the number of motor poles. And then there's some other things like torque. We can see how torque is related to speed. So if speed goes up, torque actually goes down, and if speed goes down, torque actually goes up. And we can compute that with either horsepower off the nameplate or wattage off the nameplate. And so this goes back to kind of a NEMA IEC version here, where in some cases you'll see watts, you know, more in the case of an IEC motor, or you'll see in the case of NEMA horsepower listed. And in some motors, fortunately, we see both listed on there, horsepower or watts. All right, so what does that mean? Well, that means we can do some calculations. We know we can control the frequency just with the VFD. So I want the frequency to go up and down, and we know that the RPM is equal to 120 times F over the number of motor poles. And we're assuming just a number of 4 for the number of motor poles, so we're just going to take 120F over 4 is what we're going to do. And we'll start typing these things in. I'm going to keep my annotations here for a second. And so if I do 10 hertz, 120 times 10 equals, divided by 4, I get 300 RPM for that one. So that first one is 300 RPM. And I'm gonna guess, but you know, if 30 hertz is 3 times that, I'm gonna guess this guy's probably 900 RPM, right? We'll do one more here. Let's do 45 times 120 equals that, divided by 4. I get 1350 RPM. So go right down here. I should be listing my units as I do these two. 300 RPM, 900 RPM, and 1350 RPM. What we can see is as the frequency goes up, the RPM goes up. Now a little bit different here. I've got 750. Well, what am I going to do with that? Well, let's find out here. So 750 is my RPM. So what I'll do now is I'll take 750 and I'll divide it by the P. Actually, let's see, we're going to multiply it by the P because I want to get P off of this side over here. So I'm going to multiply by 4. Gives me 3,000. And I'll divide that by 120 is 25 hertz is what my frequency would be. Now let's just take a look and see if that makes sense. I'm going to guess that this is 25 hertz based upon, well, I did a quick calculation. 25 hertz. I just want to do a check. 30 hertz was pretty close. And 900 was, yeah, I'm in the ballpark there, right? I should be bigger than 300 and less than 900, but I should be closer to 900. I definitely am in the right ballpark there. And let's do the last one here. Keep my annotations here for a second. So I've got 1650 RPMs. I'm going to multiply that by 4. Again, getting the 4 off of this side. Then I'll divide by 120. I get 55 hertz. And let's do a quick gut check on that one and make sure we think that guy's right. So 55 hertz. And so 45 hertz has 1350. I should be bigger than that, 1650, 55 hertz. I think I'm in the right ballpark there. What we can see here is as the frequency goes up, the RPMs goes up. So 10 to 30 to 45, 300 to 900 to 1350, 25 to 55, 750 to 1650 RPM. The user manual. I do like to bring up the user manual. This is something that anytime you're purchasing a drive, a drum switch, a motor starter, you're always going to get a manual with it. And if you don't get a manual with it, oops, sorry about that. If you don't get a manual with it for some reason, it's very, very easy to find a manual online, which is what I did in this case. I typed in ACS150 VFD, and this will take me right to the manual for the drive. The neat thing about this manual, once you dig into it, is all the information on it. Now, note that all the ACS150 drives are in this book, whether it's a 0.5 horsepower drive all the way up to a 5 horsepower drive, a 0.37 to a 4 kilowatt drive. So the drives are going to look almost identical. The big thing that you're going to see with a bigger motor drive is the physical size of the drive is going to get larger. And the reason why is because the amount of energy that we need to supply, the components need to dissipate more heat and higher wattage components. So because of that, these drives can get very, very large. But I can go in here, I can search it if I want. I can hit Control F and say, let's say I want to commission the drive. I can look up every place that the word commissioning is in here. And it's in there 10 different times. Commissioning the drive, purpose of the drive, all these different things. If I wanted to find out, ramp up, like ramp up for like ramp up time or something like that, I could look where ramp is in here. Let's see here, actually right here, Excel time. It looks like parameter 2202 is acceleration time and 2203 are deceleration time. I can see those right there just by typing in ramp. It showed me that where I wanted to get into there. It's also showing me some neat things about the wiring and so on and so forth. So what I will tell you is anytime you're going to work with the drive, it's going to be important to dig into that manual, especially if it's the first time you've used a particular drive or any type of control, PLC, motor drive, HMI. You want to become intimately familiar. I'd even recommend reviewing that manual for an hour or a couple hours upon receiving it before I even went ahead and installed it. It can eliminate a lot of problems later on. All right, for the ACS150, specific to our drive, many of the drives are going to look like this. When you look at the LCD, this whole area up here is where our display, our liquid crystal display, where we're going to get all of our information. The reset exit button right here, too. This is kind of like a back button. The enter button over here is kind of like a select button. When you go to program, the up and down cursors are where we're going to scroll you through the different parameters. And hitting the enter button is what's going to allow you to drill into a parameter. It is worth noting on the ACS150, sometimes you have to hold down the enter button to actually change it. Just pressing the enter button will allow you to view the parameter, but you may have to hold the button to actually change the parameter. So just keep that in the back of your mind. This guy here is the local remote. Oop, I bounced there for a second. This is the local remote button. That means I either can control it locally with the start, stop, and reverse button, and the potentiometer to control the speed, or if I put it in remote mode, then I'm going to use remote I/O wires to control those things. I can tell right now by looking in the upper left corner that this particular drive is in local mode. If I want to switch it, I press and hold the local remote button and it'll switch it to remote. This is the reverse button. I always like this button. If you look at it, it looks like this. This is a common IEC symbol for reverse. Kind of think of it like a motor shaft, either going this way or going this way. So it's the button for reverse. Start and stop. If you're controlling locally, you can start and stop your motor from the local buttons. And then the actual speed can be controlled in local from the speed potentiometer there. So I can actually already ran through all of those. You're either going to control local with the speed potentiometer, or you can control remotely using an analog input on the VFD. For operator panel, so when I talk about local control, if I don't want to control it remotely and I just want to be able to drive this thing from the operator panel, that's fine, you can do that. Step one, you'd wire up the drive in accordance with your motor nameplate. So off of that motor nameplate, you need to find volts, amps, and frequency. You'd wire up the drive in accordance with your I/O listing sheet and make sure you've got everything right. You set up your parameters for 9905, 9906, 9907. You'd energize the drive in local mode, and now you can control your VFD from that operator panel. So I can press start, the motor should run. I should press stop, the motor will stop. If I press start again, this button will allow me to reverse the direction of the motor, and then this potentiometer will allow me to make it go faster or slower based upon the speed that I want to go. 3-wire control. So this is remote control now in what I call 3-wire. And you can think of this also as like a PLC output, but let's say you don't want a PLC output. Let's say you're just going to have a start-stop button. Here's the start and here's the stop button station, and you want to control this motor. By putting your VFD application macro parameter 9902, by setting it to the number 2, you can actually place it in 3-wire. So what that means is and when we talk 2-wire, 3-wire, this screws people up sometimes. 2-wire we typically think of like a switch. 3-wire we typically think of like a push button. And the reason why we think of it like a push button is because it's momentary, and a lot of times it requires that 3rd wire. This only requires 2 wires. In 3-wire, we require that 3rd wire for a holding contact. So in 3-wire, we tell the VFD that this is going to be a momentary pulse. So we run a start button using 24 volts to digital input 1, and it's looking for a momentary pulse. And when you hit that start and release it, the motor will run. And then it's looking at the stop button as well. And when you release the stop or open the stop by pressing a normally closed push button, the motor will stop. But you'll notice this word pulse. It doesn't require a holding contact because it's in 3-wire control. It knows that you're using momentary push buttons, and you can use those. You're again going to wire up according to the motor nameplate data, just like you did before. But now you can use push buttons and switches to control the motor. Oh, and by the way, you can wire up a switch then to digital input 3, and if the switch is off, I go forward, and switch is on, I go in reverse. And digital input 4 and digital input 5 can control constant speeds. Constant speeds are, I can set up constant speeds to be like, let's say 15, 30, and 45 hertz. What that means is, maybe I want to have a slow, medium, and a fast. Well, then there's a nice little DI, we'll call this DI4 and DI5. The reason why you get 3 constant speeds is, you can have one on and the other off, or one off and the other on, or both of them on. That gives you 3 constant speeds using only 2 switches. And those are separate parameters that you can look up in the manual. And actually, well, it might be in here yet. I'm going to take a look here real quick. Let me see here, see if I can find the constant speed parameters. So if I go back into my manual, I guess I got to go back here. Oh, where is he? Oh yeah, I got to go down to ACS150. Sorry about that. There we go. If I go back to the manual for a second, let's say I want to learn a little bit more about those constant speeds, because I'm not quite clear how those work. What I would look at then is I would go into here and I go Control F and I'll write constant speeds, and I see it's on page 82. I think I can just click there and it shows it here. It says, look, you have 3 constant speeds. Constant speed 1202, 1203, and 1204. You can set those whatever you want to do. And then it actually talks about it up here. If DI3 and DI4 are off, then you're not using constant speed. If DI3 is on, then 1202 is what it's going to go to. So if I set 1202 to 15 hertz and I turn on DI3, the drive's going to go to 15 hertz. If DI4 is on, the drive's going to go to whatever constant speed 1203, parameter 1203 is set to. And parameter 1204 would be if both of them were on. So again, you scroll through your parameter list, and then when you get to that parameter, you set in the frequency you want for each one of those constant speeds is what you do. All right. Acceleration, deceleration time. So you go into parameters 1202 and 1203, and you can set the amount of acceleration and the amount of deceleration time. And these can be crazy. It could accelerate over the course of, you could take 30 seconds to go from 0 to 1,000 RPMs, or you could take 1 second to go from 0 to 1,000 RPMs. It's up to you. Whatever you plug into the acceleration time, that's going to determine how long it takes to go from whatever 0 is up to whatever your RPM that you're going is. And deceleration is just the opposite. I've got my RPM that I'm running at, and I hit stop. How long is it going to take before it gets back down to 0? So this would be accel, and this would be deceleration is what we'd be looking at. So 2202 and 2203. And one of my favorites is going to be your ramp shape. So this is what we're going to call SCurve. In a traditional drive, acceleration and deceleration only determine what I would call a trapezoidal shape. That would look like this. So this would be trapezoidal. Now the reason why we concern ourselves with trapezoidal is each one of these times you get this little corner point. That's what I would call a jerk point. That's a point when the thing is going from 0 to some speed very quickly, and it's going to jerk a little bit. And if you've got mechanical systems, belts and pulleys and bearings and gearboxes, that's a little bit hard. It's kind of like sitting at the light again. You're not hitting it to the floor maybe, but you're hitting it pretty hard. And so you're, you spin your wheels a little bit, right? We may not want to do that. We may not want to feather into that. So instead of being a trapezoidal, we like to get what's called an S-curve. An S-curve is where instead of doing what we see over here, we want to start at 0, and we want to kind of slowly feather in, and then when we get to the RPM, we want to slowly feather out. And so this is why it takes on the shape of an S, is that S-curve. To define an S-curve, again, if you set 2204 to a 0, then there is no S-curve. That's a linear ramp. That's where you just go trapezoidal. 2204 set to something other than 0 determines how long that S-curve is going to be. So I can see here, if I set the S-curve, let's say to 2 seconds, then it's going to take 2 seconds there, and it's also going to take 2 seconds here, and it's going to curve into that. It's going to curve into that, and then there's going to be a linear region where it's a constant acceleration, and then as I approach, it's going to spend 2 seconds at that last part curving in. I treat this like if you're on an elevator going to the top of a really tall skyscraper. If you just went slow, it'd be a comfortable ride, but it would take you all day to get there. So we want to go fast, but we don't want to go 0 to 1800 RPMs instantly, because if you do that on the elevator, everybody will fall to the ground and they'll be stuck on the floor, right? So we want to do this S-curve where we ramp up slowly, then we go fast, and then as we get to the target, we ramp down slowly, and we end up with this nice S-curve. So again, the amount of time we allow is that S-curve. So yeah, here's your example again. If I do no S-curve profile, then I get this little jerk point there, and there's actually one here too, because I'm starting at 0, right? So these jerk points can break things, and they're hard on equipment. If I do this nice S-curve, I get up to the same speed. It may take me a second longer to get there, depending on what that is, but the jerk at the corners are eliminated because this nice smooth transition. It's like being at the green light and feathering into your gas pedal instead of just hitting it to the floor. So let's take a look at one of these here. So we've got some ramp shape calculations, and I'm going to go from 0 to 1800 RPMs. You can see parameter 2202. This is my acceleration that I'm going to use. So I'm going to allow 8 seconds to go from 0 to 1800 RPMs, but my S-curve is 0. So my wave shape is 0. I'm not going to use any S-curve to get there. What that means is I get the jerk points. This is what we call trapezoidal. And so we can calculate the acceleration on this at these jerk points. The delta RPM over the delta T, I'm going to go 1800 RPMs, and it takes me 8 seconds to get there. So this would be 8 seconds. 1, 2, 3, 4, 5, 6, 7, 8 seconds to get there. I know I'm moving at 225 RPMs per second is what my acceleration is. My change in RPMs with respect to my change in time. And my speed eventually is going to be 1800. But to get there, I had these two jerk points. And it's going to be the same thing when I go down too with my deceleration, is I'm going to have a jerk point over there somewhere as well. I don't know what my deceleration time is right now, but I know there's going to be a jerk point there as well. If I plug in a number for 2204, this is now what I call my S-curve, the amount of time I want to take to get up to that. So at this time 0, 1, 2, 3, I'm going to create this nice S shape that curves into there. Then I get into a linear region right here. This is linear acceleration in this area. And then at the end, I'm going to S-curve out again. And again, this S-curve is nice because it's going to allow me to kind of protect against wear and tear. So my linear region, you can see I'm only linear acceleration for 2 seconds. Well, what does this mean? Oops. From 0 to 1 second. So from 0 to 1, which would be 0 here and 1 here, I calculated that I changed RPMs by 5. So I'm changing by an average of 5 RPMs per second from 0 to 1 second. And then from 0 to 2, which is right here, I said, well, now I'm up at, I don't know, maybe I'm up at, who knows, I said 50 or something like that, right? I changed by 50 RPMs over that time. So in that 1 second, I'm now changing by 50 RPMs per second. And then from that point up to here, I've changed quite a bit. And I'm calculating that it's 345. So it's 345 RPMs per second. So what I'm showing here is I'm really changing my, I'm going slow, faster, faster, faster. I'm feathering into that gas pedal to get the speed. Now in the linear region, from 3 to 5 seconds, I can see I changed quite a bit here, right? I changed from here to here in my linear region. And I don't know, this is 18, so this must be 9 of them, huh? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9. So I can see I went up by, these must be 200 each. 2, 4, 6, 8, 10. So I went up by 1,000 RPMs in the linear region. But I did that linear region in 2 seconds. So I'm accelerating very fast now. But I'm not jerking into it anymore. I'm already moving. So 1,000 RPMs over 2 seconds is 500 RPMs. So it took me 8 seconds to get up to 1,800 RPMs, just like it took me 8 seconds to get up to 1,800 RPMs here. But the jerk points have been eliminated. This is a smooth transition the whole way through. There are no more jerk points along the way. So now there's a good question that came up in class was, well, how long can I make parameter 2204? So 2204 has a maximum length. Well, if I've got 8 seconds total, right? And half of it's going to be on the ramp up and half of it's going to be on the, the ramp in, then the maximum I could have for parameter 2204 in this case would be 4 seconds, right? And the reason being is if I go 4 and 4, that actually would consume the whole thing, right? The whole acceleration time of 8 seconds. So you do have a maximum that you can use there, but it's not about that. It's about just eliminating those jerk points. So a lot of times I won't even use 3 seconds. On an 8 second, I might use a 1 second for 2204 to do some wave shaping at the front. Anything you do is going to help. But if you discover you're out in industry, you're breaking chains, you're burning up gearboxes, bad things seem to be happening. This could be a potential fix for some of those things. So you're not accelerating so fast, you're eliminating some of that jerk stuff that's going on. All right, so assume parameter 2202 is 5 seconds. So this is my Excel, right? And parameter 2204, this is my S-curve or my wave shape, is what I'll call it. Wave shape or S-curve is set to 0 seconds. So this is going to be no S-curve. Is this ramp shape trapezoidal or S-curve? Well, it's obviously trapezoidal. I have no S-curve parameter set. What is the acceleration in the linear region? Well, the whole thing's a linear region, so it's be 1,800 divided by 5. So I'll keep my annotations here and do the math real quick on my calculator. 1,800 divided by 5. It would appear to be 360. Oh, I lost my sheet there. There we go. It appears to be, 360 RPMs per second. Okay, because this was RPMs over the number of seconds. Okay, 360 RPMs per second, or probably better written as, when we write it like that, 360 RPM per second. All right, assume parameter 22 is 10 seconds. That's your XL. 2203 is 4 seconds. That's your decel. So this is the XL. Now we've also given us our deceleration as well. I wonder if I've got these. Oh no, I don't have the answers in here. That's fine though. And then I see that 2204 is my SCurve, is 2 seconds. First off, is a ramp-shaped trapezoidal S-curve? Well, we know it's S-curve. Why? Because we've actually got the parameters set now, right? How many seconds does the linear region last during acceleration? Well, acceleration is 10 seconds. So I've got 2 seconds of S, and I've got 2 seconds of S, and then I've got the linear region in between. So 10 minus 2 is 8, minus 2 is 6. So 6 seconds in the linear region. And then I have S-curve on either side of the 2 seconds. So this would be for the XL side. Okay. So linear region lasts for 6 seconds. How many seconds does linear region last during deceleration? Well, deceleration is only 4 seconds. So I still am going to have my 2 seconds. Oop, I drew it the wrong way. 2 seconds. And I'm still going to have my 2 seconds here. But I only have a total of 4 seconds for deceleration. I actually should be drawing these backwards altogether. Decel should be going this way, right? But if I'm 2 and 2 for decel and I only have 4, the linear region is what? It's 0 seconds. Because 2 seconds and 2 seconds is my entire deceleration period. So the whole thing is going to be S-curved. There we go. All right, so now moving on to the VFD PLC interface. So when I'm working with a VFD and a PLC, let me get over here and find this little guy. Move him up out of the way. There we go. The ABB standard macro allows digital control and analog I/O from a PLC control. Now it could also from switches or potentiometers, but basically I'm going to treat these switches like PLC outputs. So my PLC outputs, instead of coming from 24 and going through a switch, these will be PLC outputs like Q1 and Q2 and Q3, or if you're an Allen Bradley guy, you know, O:2/0 or something like that. These will be PLC digital outputs feeding directly into these digital inputs on the drive. And then my analog input on the drive would be analog from the PLC going right into there. So I have digital outputs from the PLC going to digital inputs on the drive, analog outputs on the PLC going to analog inputs on the drive. So wire up my I/O in accordance with the PLC I/O listing sheet, wire the drive in accordance with the I/O listing sheet, set up the VFD parameters. 9902 application macro 1 is going to give me this wiring routine. 9905 through 9907 is going to give me my motor nameplate data. And then I can use HMI, PLC outputs to drive VFD inputs. The analog interface, this is important for using analog, it's important there's a little dip switch on the drive itself. Down in the bottom lower corner, I think. Let me just see if I can pull up a picture of the drive. Here he is. Yeah, this little dip switch is right down here, and there's like an I and a U there, which stands for current and voltage. You know, think of it as an I and a V, but essentially current and voltage. So in our case, if we want to use an analog input of 0 to 10 volts, I want to make sure that little dip switch is down to the V or the U is what they're going to look at there. And then I can either use a potentiometer to control the voltage, or in my case, I'm going to use a PLC analog output to run 0 to 10 volts into the analog input on the drive. And then that 0 to 60 hertz could be equivalent to 0 to 1800 RPMs if I'm using a 4-pole motor. So that's an important thing on wiring this guy up. All right, so how does this all fit in? And before I get into the details of this, I do want to show you the ABB drive suite here. The little drives that we have in the lab, small pictures, I think you're looking at them right here, would be the one that we have in the lab. But it gives you an idea of the whole family. You know, this is, let's say, you know, 1/2 horsepower drive, right? Something like this might be, you know, might be a 100 horsepower drive. You know, and something like this guy up here might be a 5,000 horsepower drive. You can get the idea of how the size, and I don't know off the top of my head on these drives, but I will tell you it's proportional. The size is proportional to the size of the motor that you're going to run with this thing, right? All right, so what does the HMI do in the big scheme of our system? Well, it sets bits. So we set bits inside the PLC. The PLC then can use those bits to turn on outputs, and then those digital outputs can run over to the HMI, or excuse me, over to the VFD. That's then going to turn the motor on, turn the motor off. Could reverse the motor, could go to a constant speed on the motor. We also are going to use analog, so I could put a numeric input on in my HMI. Say I want to go 900 RPMs. That 900 RPMs then equates to a 5-volt signal coming out of the PLC that's going to go over to the HMI. That 5-volt signal then is going to take me from 1800 RPMs back down to 900 RPMs. All of this because the VFD, oh yeah, so I want to be careful of the HMI there. 5 volts from the PLC to the VFD is what we're trying to do there. And so that application macro says, okay, well, I'm going to look at this terminal and look for voltage, and that voltage is going to tell me what speed I want to go. And it should be that simple. So if we go back to the one of the very first slides in here, this guy right here, I hit a start button. That start button tags a bit. I'll call that bit I0.0. Okay. Inside the HMI or inside the PLC somewhere, I find out, or it doesn't even be I0.0. It could be M0.0. It could be just a memory location. M0.0 goes to Q0.0. Come to discover Q0.0 then is wired up to the start bit in an application macro on the motor drive. That then turns the motor on. Okay, and maybe I've got another bit, an M0.1 here that I want to reverse my motor. And M0.1 from the HMI goes over to Q0.1. And Q0.1 then is wired up. Q0.1 is wired up to the reverse. And now all of a sudden I go in reverse direction. And you can see I could type in a numeric, right? I could plug a numeric into, let's say, an MW, a word location. So I plug in a numeric of, I want, 50%. And the PLC then makes a decision and says, okay, well, 50% means an analog output of, I don't know, 16,000. Oops. Means an analog output of 16,000. So it writes 16,000 to an analog output, which then sends a 5-volt signal over to the analog input on the drive, and now the motor runs at 900 RPMs. So you get an idea of how bits can turn on outputs that can send voltages to motor drives, and this is all going to be discrete and analog I/O that we're sending right now, but we can also do this over networks too, so that the PLC, instead of sending a 24-volt signal over to the VFD to turn on, it could just send over a 1 or a 0 over to the VFD, over industrial Ethernet or RS-232 or RS-485 to just turn on that variable frequency drive. So with that concludes the very basic lesson on VFDs. I hope this is a help, and I'll see you guys in the lab. Thanks.